Okay, got to go over this homework question here. This is based off of graph number 3 from the transit graph thing. So, let's see what we got. Planet radius. So, let's look at the graph here. This depends on how much of the light's actually being dimmed. So, let's see. Not quite halfway between the lines. I don't think it is. I think it's like slightly less. Slightly less. I'll say 0.24. Okay, so that's what I would say. And maybe you're just going to say 0.25. That's fine, but, so your answer is going to be a little bit bigger. But I'm going to say 0.24. So that's 0.24% decrease, which therefore means that delta F, again, because that's a percent, is 0.0024. Okay, so you got to be careful about that. Radius of the star is, again, 0.683 times the radius of the sun, so that's 6.955 times 10 to the 8. So, the radius there is, I always forget to bring a calculator before I start this. 0.683 times 6.955, 12123. Okay, 475, basically. Please fit. Okay, I can't fit the meters in there, but oh well. Okay, so we have delta F equals R planet squared divided by R star squared. So we have 0.0024 equals R planet squared divided by 4.75 times 10 to the 8 squared. So squaring that gives you, let's see, 2.2565. That's the 3, 6, 9, 12, 15. Okay, 17. So 2, 17. Okay. Multiply that up. So times 0.0024. Okay, and that becomes, wait, 3, 6, 9, 12. Okay, so it's 14. Yeah. Okay, so 5.4156 times 10 to the 14 equals R planet squared. So R planet equals square root of this. Okay, 2.327 times 10 to the 7. And just to get this in Earth radii, I guess I didn't clarify that's what I wanted in, but it's still. Gonna divide by the radius of the Earth, and you get 3.65. So that's a little bit smaller than Neptune. A little bit smaller. Neptune and Uranus are both about 4. I know it's like 3.9 versus 3.8 or something, so yeah, it's a little bit smaller than Neptune. Okay, so a little bit smaller than Neptune. Okay, so now where are we on? We're on orbital radius. Okay, so we have that here squared equals the semi-major axis cubed divided by m star. Okay, so we have m star, that's 0.81. The year. Okay, so let's look at the graph again. Okay, so let's see. We start a little bit less than, tiny bit less than 3, and it goes to a little bit more less than 8, and then 13. Yeah, see, it's getting a little bit less and less each time, like away from the line. So, okay, 3 to 8. Yeah, basically, it's 3 to 8, but like a tiny bit less than that. So it's a little bit less than 5. I guess if you could probably put 5 days and say that's close enough. I'm going to be picky and say that it's 4.9 days. So, wait, no. T year. So it's 4.9 days, but again, you have to put this in years, so divide by 365. What am I, 365? Okay, 0.0134. Okay, so that's what we're going to use for t here. So we have 0.0134 squared equals a sm cubed divided by m star, which is 0.81. Okay, so square this. 0.0008, okay. So now times 0.81. Okay, 1.4. Oops. Okay. And cube root equals 0.05265. Yeah, I'll do 5265. 0.5265 AU. So a bit more than 5% of the distance. And we need to convert this to meters. Again, I technically don't ask you to do this, but you need it to be in meters for the equilibrium temperature. So this you kind of have to do. So this is going to be times 1.662. Okay. So 7.877 times 10 to the 9. Yeah. Okay. Now, equilibrium temperature. Probably should change. I probably stop writing R orbit and just write A SM because that is what this is in this case. But oh well. Okay, so temperature of the star is 4780 times the radius of the star, which I have up here, 4.75 times 10 to the 8. That's 9. Okay, divided by 2 times 0.877 times 10 to 9. All right. So, I'm gonna copy all this down here. Okay. So multiplying this by 2 times 2. Okay, 1.5754. This is another 10. Okay, then we're going to divide that by that. So divided by 475. That. And the inverse of that. So 0.03015. And I got square root it. Okay, 0.17364. And we get an equilibrium temperature of 830 Kelvin. Almost exactly. Kind of nice. Which if you want this in other things, so that's 557 degrees Celsius, which is 1034.6 Fahrenheit. Which, considering a lot of these other ones we looked at were like, let's see, what were these other ones? Yeah, 3,400. This one was 2,000. Like, that's not so bad. It's a lot better than the others anyway. So here you have something that's slightly smaller than Neptune that's over 1,000 degrees. Congratulations. I don't know. Whatever. Yeah. Okay. We are now going to move on. So, the last couple things we're all talking about, okay, hey, we've been finding planets around other stars, and let's kind of figure out how we do that, and some numbers and information we can get from that. But then, of course, that gets the question that people want to ask about, which is aliens. So, sure, we can find all these planets, but could there be life on them? And that's the big question, isn't it? So, your warm-up question is just straightforward and simple. Do you think aliens exist? This is just honest personal opinion about whether or not you think this is true. Do you think aliens exist? And you may want to clarify your answer. Besides just saying yes or no, you may want to say, you know, maybe you think that like maybe like living things exist, but there's no intelligent life, or maybe whatever. If you want to clarify, however you want to think about it, whatever you want to think. So just honest, personal. I believe blah. Just let me know what you think. I'm curious. Okay, so there isn't a right answer for this because we don't know, right? Obviously, so it's really just comes down to personal belief. Um, here's my opinion, okay? And again, I'm not saying you have to agree with me for this. This is very much an opinion. I think, um, it's a near guarantee that some type of life exists somewhere. Okay. In my sense, it's purely a numbers game. Okay. Um, there's something I believe I saw that like in our galaxy alone, based on our data of uh, Kepler, which is the telescope that we use to find a lot of the exoplanets and that kind of stuff, um, we think that there may be like 200 billion Earth-like planets in our galaxy. Now, Earth-like, that doesn't mean they all are like definitely have life on them, but like even if 1% of them do, then that's 2 billion planets with life on them. You know what I mean? So like I think just by pure numbers there is, that's just in the galaxy, let alone the universe, right? So I think it's almost inevitable just by pure numbers that there is some life somewhere. The real question then is how advanced is it? And that's a big question. Again, I like to tend to think that like again thinking back to pure numbers, like again, okay, so 1% of the planets that could have life do, like what if one, okay, that's 2 billion. What if like, and you say, oh, what if intelligent life is super rare? It's 1 in a million. Well, if you have 2 billion things and it's a 1 in a million shot, well, that means you have 2,000. So, if you want to think of it that way, and then of course, if you talk about that, then the question gets into like, well, then how come we don't see them? Because if you think there is intelligent life, we would see some evidence of them, and then that's its own kind of conversation. So it's a very complicated thing. I don't have a good answer for this. My best answer would be there is some life somewhere, almost guaranteed. Is it intelligent? That's a giant question. And I'll kind of share my own personal opinion on this. This goes a little bit more beyond just scientific reasoning, and this is just like, I believe this is true because I think it sounds nice. I'll share that later. But for now, I mean, there isn't really an answer to give for this. So I'll say, in my opinion, it is a near guarantee that some life is out there somewhere. But again, you do not have to agree with that statement, okay? So don't feel like, oh, I'm wrong if, don't agree with Great Sage Berrigan or whatever. So, yeah. So, okay, let's actually talk about this. How can we try to put science to talk about aliens? And it's really hard because, well, there's a couple things that make this really difficult. The one of them is that what even is life? Right? You would think, well, I know that like my dog is alive. I know that like, this glass of water here is not. But like, it gets complicated because, for example, our virus is alive, right? That's what's happening right now, and we don't really have a good answer for that because you might think, well, what do you mean? Well. And we're going to say, well, what is the definition of life? The thing is, we don't really have a definition of life because we don't really know. So the best thing that I've seen is that, like, it is a thing that processes energy on its own. It kind of takes an energy and uses it to continue its own functions. It reproduces. That might be it, actually. I don't remember. But, like, it's... And if you think about it, like, viruses, they do move around. They do reproduce, they can use energy, process energy, but they can't do it by themselves. They have to parasitize other things to do it. So it's complicated. It's a really hard thing to say, like, our virus is alive. And there could conceivably be situations where if we think about like alien life, where it's like, do we even like would we even know what an alien is if even if we're staring at it, right? Because is its form of living even what we know about, right? So so it's life of alien life. Okay, and the first is what even is life? Because we don't know. We don't have a really good definition for that. And again, even not talking about like small scale viruses, but you could go a step further. For example, is an ant colony life, right? And you think, well, it's made of life. Yeah, but like, is it itself a living thing, right? And it's like, you could probably say, well, I mean, it's ants together and the ants are alive, so therefore, okay, sure. Okay, is a rainforest a living thing, right? And you're like, well, the trees are alive, so okay, sure. And like animals are involved, those are alive, okay. But then the question is, well, is the earth a living thing? Right, and you can keep, so this almost feels like religious, almost, if you want to go that route. But like, you see what I mean? It's so hard to define this in different ways, and it's very complicated. And it's not if you think like that would be a really simple question, like, well, of course we know what, like, this is alive, this is dead, but it's really hard to really narrow in and get specific definitions for this. So that's one. And then the second question is, what does life actually need to survive? Okay, and we don't know this 100% either. We have some things where we're like, okay, we are certain about like two things. Actually, we're not even certain about those two things. We're certain about one thing. And that one thing is an energy source. You need some type of energy. On the Earth, most of that is the sun. Okay. The sun provides energy to the Earth. That, of course, is used by photosynthesis. And then that gives us plants and also photosynthetic bacteria. And then other creatures end up eating the plants or the photosynthetic bacteria, and then creatures eat those creatures. So it's that, but the base of the food is the energy from the sun. That's not all of it though. There are chemotrophs, which is stuff that basically uses chemicals for their energy. They basically, if you've taken chemistry, you know how like if you certain molecules, they have energy that bonds them together. You can actually break those apart and give yourself energy that way. That's actually when humans are eating meat, or not even meat, but plants or anything. That's what's happening in our digestive system. Okay, so that's the whole thing about like, oh, calories and stuff. It's energy from the bonds of the molecules and atoms, fundamentally all the way down. But again, the process of that is ultimately started from the sun. But you have things that exist without the sun that do that. So, for example, there are deep sea vents that are way deep underwater, thousands of feet underwater, where sunlight does not reach at all. There is no photosynthesis, but you have these sulfur dioxide vents that are basically spewing this out into the ocean, and there are bacteria that basically use the sulfur dioxide, and they take that in, they break it apart, and get energy that way. And then you have other macroscopic organisms that feed off of those. So you don't have to have it be the sun, but you need something, okay? Because you need some sort of energy, because you need energy to do things. Living things do things, okay? They need to do things. They need to reproduce. They need to eat. You need energy to get energy, but yeah. So we know we need that. And we are almost certain that you need some sort of mixing agent, okay? And what I mean by that is you need some sort of environment that allows mixing of atoms and molecules really easily. Namely, you need some sort of liquid, a stable liquid that allows for dissolving, mixing, all that kind of stuff. And the best option for that is water. For a couple of reasons. One is that it is it's fairly common, right? People talk about, oh, like, water's not common. Well, it is actually fairly common. Again, compare like water to like, I don't know, hydrogen peroxide is a lot rarer naturally than water, right? So yeah, so it actually is relatively common. It is all, it's H2O. It's not exactly a very difficult molecule to assemble. And also the fact that it's a polar molecule. So again, this gets into a chemistry thing. So because of how it's the whole Mickey Mouse ears kind of design of the water molecule. You have the positive hydrogen ions on one end and the negative oxygen ion on the other end. So this allows water to sort of stick to itself. And this helps a lot in terms of like mixing things and moving things around where things get stuck in the water and the water moves it all over the place. So that's very helpful as well. So that's why when we talk about alien life, people often talk about looking for liquid water, and we're going to get into that a little bit as well. So that's kind of what we are. That's all that we can say we're actually. One other thing we're confident in: we need a solid surface. Okay, that does not mean it has to be like dry land, because of course, for example, if we think life started actually in the ocean, when we know at least macroscopic life we know started in the ocean. But we're pretty sure microscopic did too. But you need the water to like to have liquid water. You need to be on top of a surface, right? So you need some sort of surface. So gas planets are pretty much. We think that they're not going to have life on them. There is some vague ideas about some like floating organisms, but it seems very unlikely. So this is why we look for rocky planets and not gas planets that would have liquid. They would have a surface, so you need liquid water. But from there, we don't know a lot past that. Okay, for example, we think that. Actually, one more thing you need time. Okay, you need time for things to happen, and so you need to have at least a decent amount of time where nothing catastrophic happens, right? If you have so this is, for example, O stars, right? The O and the B stars, the really big bright stars, those burn out after a few million years. That's not that much time, right? Because again, think about how long it took for life to evolve on Earth. So if your star is going to explode in 10 million years, then you're not going to have any life on the planet to really do anything in 10 million years. So yeah, that's kind of an issue as well. And there's a few other things that kind of go with that as well. I'll get into a little bit. But that's why we think that when we're looking for life around planets or other stars, we're usually not looking at stars that are much bigger than our own. Because again, the bigger stars than our own, then they live less time. So that's the kind of main thing with that. But again, there's a lot of other stuff that could potentially be important that we don't know about. For example, there's one idea that we might need a large moon. Okay, and the idea is that, well, if you have a large moon, it does two things. One, it sort of stabilizes the planet from just wildly tilting around. That's an idea, and that could be important in terms of seasons and weather being kind of stable. Also, it could if there is a meteor asteroid that comes by, the moon's gravity could sort of mess that up and not hit the Earth as often or whatever. There's also an idea that, hey, if you have you want a large gas giant close-ish, but not too close nearby, so again, think Jupiter with the Earth, to do a similar thing, stabilize orbits, and also if any sort of asteroid or comet might hit us, instead might get messed up by Jupiter. That's an idea. We don't know, though. There's also an idea about ultraviolet light, right? So, for example, ultraviolet light is damaging to our organic material, right? The whole sunburn thing. Is that universal, right? Is that something that would basically always be true, that any sort of organic compound is affected by ultraviolet light? Or is it just that that's how life evolved here and we didn't really have to worry about it because there is not that much ultraviolet light from our sun? Where if you have a star that emits more ultraviolet light, does that mean therefore life cannot really survive there? Or would it just evolve to deal with it? We don't know, right? So there's a lot of things we don't know about here, and there's a lot of stuff which you can get at that we just don't really know. And again, the more things you add on, where you say, oh, we need this, and we need this, and we need this, and we need this, well, that means the rarer life is going to be, because you're going to have less planets that actually fit all of those criteria, right? If you have 3 things you need, well, there's a lot of options, but if you have 35 things you need, there's going to be a lot less options, right? So we don't know. And then the third thing that's an issue is we only have one example, okay? And so this is something that's also very challenging, is that we only know of life existing here, okay? Now, granted, there's a lot of different environments of life here, which is helpful, but we only have one example of life. And so it's really hard to extrapolate that to everywhere else, right? For example, even if, let's say, life does totally exist in the universe, in the galaxy, and it's somewhat common-ish, but if that's even true, is the life on Earth normal, or is it weird, right? We don't know. So is the conditions that gave rise to life here, is that how it usually is, or is our planet weird in that actually most life does things completely different, but we just happen to evolve this way? We have no idea. So we have no idea because we only have one thing to look at, we don't know, right? And so that's a big issue as well. And so a lot of things, for example, the large moon and things like that, the argument that's kind of against that sort of stuff is that why are you, just because the Earth has that, why are you assuming we need that? Right? Maybe we don't need that because we don't know how evolution. I mean, we know the basis of evolution, but we don't know how it's going to work if your environment is very different. So we don't know if you need it, those things or not. Maybe we're being very anthropocentric, which is that's the term for we're basing it off of we're assuming that us as humans on the Earth are, well, obviously this is how it is. This is normal because we are what it is, but we don't know if we're normal. Maybe we're super weird freaks, and like every other alien life is just like, what's those weird Earth people? They're weird heads, like, you know what I mean? We don't know. So these are kind of three main issues in terms of how that comes. But the main things, things that we're quite certain that a planet needs to have life are an energy source, a rocky surface, and liquid water. Okay, so those are the main things. So the energy source is a star. Now, again, stars, any sort of star could theoretically work. The issue is that for the biggest stars, they live much less. They live much shorter lives. So any star could theoretically work as an energy source, but bigger and hotter stars live much shorter lives. So most, and they're also rarer, to be fair. So it's like, why are we looking for all these planets around all these B stars that could have all this life on them? It's like, yeah, but there's like 0.01% of them. So like, why are we looking at those stars? We should look at the much more common ones. So most people don't really worry about O, B, or A stars. F stars, those can live about 1 billion years. So that's still kind of short, honestly. But you could maybe get something from that. But yeah, so most people look at just G, K, and M stars. In terms of that. Now, and so okay. Now, a rocky surface. So, in order to have a rocky surface, you need to be a rocky planet. And so then the question is, well, how do you know if a planet's rocky or gaseous? Now, the fact that, like, Jupiter, Saturn, Uranus, and Neptune are the big planets of the solar system, and they are gassy planets, and that Earth, Mercury, Mars, Venus are the smaller planets, they are rocky, that seems to be, as far as everything we have seen, that seems to be true, okay? So, rocky planets are smaller planets than gas ones. So, you're not going to have a planet the size of Jupiter that's a rocky planet, and you're not going to have a Mercury planet that's gassy. That's just not going to happen. We've never seen any evidence of that at all. But the question is, so Earth is the biggest rocky planet in our solar system. Neptune is the smallest gaseous planet. The question is, where does that transition occur? Right? If you were to get a planet, if you were to scale a planet bigger than Earth, when does it become a gas planet? And also, what does that transition look like? Right? It's not like, oh, only rocky, only rocky, only rocky, only rocky, gas. It doesn't work like that. And basically, it's when you get to a big enough size, when your gravity is strong enough to really get in such a big and thick atmosphere that it sort of overwhelms any sort of rocky elements inside. And basically, the pressure inside is enough to sort of like screw up any sort of like surface, and it just sort of kind of dissolves into some sort of gradient mess, and it gets kind of complicated that way. So the question is, where is the size boundary between rocky and gaseous planets? We know it must be between Earth and Neptune, okay? So Earth is the largest rocky planet in our solar system at 1 Earth radius, obviously. And Neptune is the smallest gaseous planet in our solar system at about 4 Earth radii. So the transition must be somewhere in between. Okay. Now, for example, the problem we did up here, involved, yeah, this planet was 3.65 times the radius of the Earth. So the question is, for example, is this one a rocky or gaseous planet? And you may think, well, it's pretty close to Neptune, so it's probably gaseous, and yeah, it probably is. But what if, for example, I had a planet that was twice the size of Earth, right? Well, is that rocky? Is it gaseous? I don't know, right? So I've only actually seen this just talked about once, but some group, and you can kind of maybe look into this because I don't remember the details, but some group looked at all exoplanets that we found, obviously, that were between the size of Earth and Neptune, where we knew both their radii and their masses. Okay, so if we can know both of these, then we can then find their densities. Okay, and if you're a gaseous planet, you're going to have a small density, whereas the rocky planets can have a large density, right? So Earth's density is noticeably larger than Neptune's. I don't remember what it is at the top of my head. Let me see if I can get that number actually here. So let's find out. Earth's was like 5.8, I think. Orbit. Well, I don't care about the orbits. I care about. Wait. Mean density 5.5. Okay. So Earth's 5.5, and Neptune is density 1.6. Yeah, so that's a pretty big difference, right? So so they looked at this, their masses, and masses. Okay. And here's what they did. They noticed that as you increase in size from the Earth, your density increases, okay? And you may think, well, wait a minute, like, just because it's bigger doesn't mean it's more dense. No, but if you do think of this in terms of, like, a thing of rocks, as you add more rocks onto your thing, you add more mass, it therefore means that you kind of compress more, you have more mass pushing in, so it kind of does make sense your density actually would increase as you get bigger. As a general, for example, Mercury is more dense than Mars, even though it's smaller. So it's not perfect, but this is a rough average description of what they saw. So the density increases until the planets are about 1.5 times the radius of the Earth. Then, as you get bigger, the density decreases. Okay, so basically what this seems to imply is that once you get to about 1.5 times the size of Earth, you start turning into a gas planet. Okay, and we still don't really know exactly what this would look like. For example, a planet that's 1.6 Earth radii, what would that actually look like? Would it just still look like, a rocky planet and it has an actual surface? It's just this atmosphere is really thick and really large? We don't know. There's ideas also that, like, especially if this planet could have liquid water, it could be some sort of water ocean planet where where the entire planet is covered by an ocean that's like hundreds of miles deep, which, if you don't know, our ocean is not hundreds of miles deep. So maybe that would sort of lower the density of it because water is less dense than rock. So that's an idea, but we don't know. We don't really know what this exactly looks like, but this does narrow things down. So again, you think, a planet that's 3 times the radius of the Earth is probably not a rocky planet, so it's probably not really going to work. So that's sort of kind of gets the discussion there and how that could work. And again, it's all different, right? Just because you have, let's say, you have 2 planets that are both 1.5 times the size of Earth, they don't have to have the same mass, right? One could be more massive, it could be more rocky, one can be a little bit more gaseous. We don't really know. So, but it's at least that kind of gives us an idea of this sort of transition and how this would look like. Okay, so we've talked about the stars, rocky planets, then talk about is liquid water. So, to have liquid water, you need both, water, obviously, and it needs to be the right temperature and pressure. Okay. Now, the pressure comes into play in terms of the atmosphere. So the pressure is determined by the atmosphere. So you need at least a somewhat decent atmosphere in order to have liquid water, right? Even if the moon, maybe you found a place on the moon that has like the right temperature somehow, your water is going to immediately evaporate because the pressure's almost nothing. So you need at least some sort of pressure. And the atmosphere also helps the temperature as well. So an atmosphere helps warm the planet up a bit. It also stabilizes the temperature. So for example, I said about how Mercury was super hot on the day side, super cold on the night side. If you had an atmosphere there, it would help spread the heat from the day side over to the night side, right? And it would help spread that out more. So the atmosphere also is important, involves the temperature. So the atmosphere is important regarding temperature, but I don't know if mainly is the right word, but it's largely caused by the planet's distance from its star. Okay, and so this is where we get to something called the habitable zone. Okay, so the habitable zone is it's the region from a star where the temperature is right for liquid water to occur. Okay, now it's a region, right? Because for example, if the Earth was a little bit closer, you could still have liquid water. And still be fine. If it was a little bit further, it could still liquid water still be fine as well. For example, we think Mars had liquid water. The reason Mars doesn't have liquid water now is we think more to the fact that it's small, so the whole magnetic field stopped working, and more so the core cooled quicker, so the magnetic field stopped working, so the atmosphere started going away. So there, because the pressure went away, the water vaporized, and also the temperature went down, so it also froze it. So yeah, but for example, there's total ideas that if we just put Earth where Mars was, the fact that it's just a bigger planet means you could probably have liquid water that would probably be okay there. I mean, we would probably not be happy because it would be very cold, but like you would have liquid water, you could probably have some life there. So, so around the sun, this is kind of a general. This is kind of a again, people argue about this specifically, what this is, but we think the habitable zone is from about 0.7 AU to 2 AU. Okay, so that's what we think, but again, it's very much up in the air in terms of how exactly true this is and what the upper and lower limits of this are. I've seen some things that say, hey, if you have a good enough atmosphere and everything works out really well, maybe you could even have something all the way to 3 AU that's actually still warm enough to have liquid water. So it's a range for how this could work. These numbers are sort of the general ones that I've seen accepted, but again, there's a big range of what could be true or not. So, but again, this is around the sun. So smaller stars, their habitable zone is going to be much closer. Okay, so smaller stars would have habitable zones that are much closer. And actually, an approximation for this, a decent approximation is to take a star's luminosity in solar luminosities, square root it, and multiply by the boundary numbers around the sun to approximate the habitable zone. Okay, so what I mean by that is, let's look up a star. Let's look up TRAPPIST-1, because that's, again, remember that was a star that was kind of special. Okay, TRAPPIST-1, its luminosity. Where do we want that? Let's see, luminosity. Where's that? Oh, luminosity. There it is. Okay, so 0.000522. Okay, so we want to square root this. So TRAPPIST-1 L equals, what was it? 3 zeros, 522. So what we want to do is square root this. Oops, it's 522. Okay. 0.123522. Okay, so square root it. and we get 0.0, I'll do 228473. Right? Yeah, that's good enough. Okay, so then you want to take this number and multiply it by these here. So this would mean your lower bound is 0.228473 times 0.7. And your upper bound times 2 or 5.7. Okay, so that's your bound for TRAPPIST-1. Basically, in order for a planet to have liquid water on its surface, we think you would need to be in roughly this range around TRAPPIST-1. So, and you can see actually because TRAPPIST has all these. Where's your sort of, here we go. Okay, here's your axis. So what do we have? We want between 0.16 and 0.016 and 0.045. So, okay, so that gives D, E, and F as potentially inside the habitable zone. And all of these are, F is actually the closest to D. Anyway, so you can see that how this could work in that sense. And again, of course, this is all approximations. We don't even just because just because a planet's in the habitable zone, first of all, it just needs water to be there, right? So it could just be a planet. Oh, the temperature's right, but there's just no water on it. Or it could be a Mars situation where the planet was too small to hold on to its atmosphere and stuff for long enough. So that's another idea. So this is not an end-all be-all. It's not like, oh, if the planet's in the habitable zone, it definitely has life, right? We don't know that. And here's sort of an image I've found, which sort of shows. So here's sort of here's basically showing the different temperature of the stars, and then the starlight on a planet relative to the starlight on Earth. So obviously, for closer in, you have more starlight. So, oh yeah, see here's TRAPPIST. These are TRAPPIST 1D, 1E, 1F. I think there's 1G also. You can see that instance there. And then all these other planets here. If it just has like 438, 269, those are all. It's Kepler 438b or Kepler 560b. This is Gliese 667cc. So these are all ideas about potential planets that are around. You can see Venus is outside of that, and then Mars. See again, we think Mars could have been habitable if it just was bigger. And also the planet sizes are all sort of demonstrated based on the size of them drawn here too. So, oh, there's Proxima Centauri b. Remember that one we talked about before. So, yeah. This is just an example of kind of how this could work. But, even then, like, this is just the bare basics, right? There's so much more that we can get into. For one thing, this is the thing that's actually really important. So, most of these planets you notice are around small stars, and that's partly because there's a lot more of these M stars, and also because the star is smaller, it's easier for us to see the planet going in front of it. So, for planets going around small stars, they have to be so close in order to have liquid water that the planets are almost certainly tidally locked. Okay, so what does that mean? What does tidally locked mean? Tidally locked means that one side of the planet always faces the sun. Okay, so basically, just like how one side of the moon always faces the Earth, so that you'd say the moon is tidally locked to the Earth. So in these cases, that's because this has to do with tidal forces and gravity. It's very complicated in terms of the exact math behind it. But if you are close enough to an object that's massive enough, the gravity will be strong enough to basically lock you in place. Okay, where a planet, where one side of the planet will always be facing toward its star. Okay, now this is a very big question in terms of habitability. are these planets habitable? Because again, remember the equilibrium temperature thing and the whole thing with liquid water. That's an average temperature. So if you have one side always in the daytime and one side always at nighttime, well, then neither of them are going to be the average, right? One of them is going to be hotter, one of them is going to be colder. Again, a thicker atmosphere can help spread that heat around, so it's not like Mercury, but it's not going to be equal. And so that gets to a lot of questions about how does habitability work. Is it, and also even there, for example, where is the water on the planet, right? If the water is all like on the day side, well, then it's just going to all get evaporated. But then if it gets evaporated, well, that means it could spread to the atmosphere and then go to the cold side, and then it could like rain, but then it would freeze. So it's so complicated, right? This gets so complicated. And also, we don't have an example of a planet that's like this in our solar system. Mercury is kind of close. It's in a 2 to 3 lock, not a 1 to 1 lock. Again, it's a resin thing. It's complicated to get. So it is actually, Mercury is sort of locked with the sun, but it's in a way where it rotates 3 times for every twice it goes around the sun, whereas full tidal locking is basically the planet rotates once as it goes around the sun. So it's rotating with its orbit, basically. And we do not have a planet that does that. The best thing we ever get, and then the moon does that with the Earth, but that's not helpful in terms of talking about like how like a climate would work there. We have just vague models and ideas in terms of how a climate would work on a tidally locked planet, and that's super interesting. And there's a ton you get into that. It's a big question. And again, like 75% of all stars are M stars. So that means that like if you assume the numbers would be that way, then 75% of like all planets and all habitable planets would be around these stars, which means they would be tidally locked. So we have no idea like if this is even possible, right? But again, the question is like, and some people have just said that like it's not possible. But again, then the question is, are we thinking too much that, oh, Earth's way is the way, right? It's so complicated, we don't know. But it's definitely something you have to think about. And it would be really weird, because some people say, oh, life could exist, but like only on like a thin sort of twilight strip between the two halves, which would be interesting. Your world is in perpetual twilight, where you see a red-orange star just sitting low to the horizon and it never moves. Like, that'd be super weird, because then think about, like, you have aliens or whatever that grow up there, and they're just like, yeah, there's just this, there's our light in the sky, it's always there. And then if they came to Earth, they'd be like, what the hell, your light moves? What? You know, it's like, they'd be so trippy with that. And, like, I don't know, I had this, like, really weird thought about it, where I was like, what if you had, oh, well, another thing is, oh, even before I get to that, I thought about in terms of trees. Right? Trees and all plants in general, they sort of grow up and out so that they will grow up just to get closer to the sun, and also so that like other things also don't try to grow on top of them. But they grow out because the sun could be in any direction. So they want to sort of spread out in all directions so that they could get to the sun wherever it is. But if your star just stays in the same place in the sky, you don't have to grow up, right? You don't have to go. You have to grow up. But you don't have to grow out like that. So I was thinking, like, you could have these like trees that are almost like look like satellite dishes, right? They're just like pointed at the sun, because it's like, there's my light right there. I just need to point there. So like, that's, you know, interesting idea for that. But then I thought, like, what if this is getting almost philosophical here? What if you had, and again, I'm not even saying this is possible in a sense, but what if you had some sort of intelligent civilization that lives on the day side of a tidally locked planet? Okay, again, let's assume that it works and it's only on the day side. And the night side's too cold for them to live. They can't go over there. It's just too cold. If you think about think about your life as in perpetual daylight. And let's also say that there's no moons around this planet, because let's just say there aren't any. If you look up into the sky, of course, and there's clouds and stuff like that, but past that, all you would see is the sun. You would never see any stars. And the sky would never change in that sense. So, would you even, like, have a curiosity about, like, the universe, right? Because, like, that's how we have curiosity about the universe, is because we looked up at the night sky. We see stars. We see the moon. We see, you know, the whole thing about planets was that, hey, there's these things that look like stars, but they're moving around in the sky. Like, you know, so how would that work in terms of, like, how would that, you know, fulfill their, like, civilization in terms of their technology and stuff? Would they just like think like, yeah, okay, there's our light, whatever, I don't care. Why would I care about like going to explore the universe? Because like, who cares, right? And then I also had a really weird thinking about like, how would they tell time? Because, you know, we tell time based on how the sun moves through the sky, right? That's how we do it. And even we can tell years by how by looking at the night sky, we can sort of tell as the Earth like kind of moves around the sun and stuff. And so I was like, well, okay, what if you also, and again, this, you had the sun never moves in the sky, so like you don't have like hours and like days and stuff. That's just not a thing. And then you could have it where I don't know, the planet has like no tilt, right? In which case you wouldn't be able to tell seasons. There would be no like yearly variation of seasons. So then like how do you tell time? So like that's a giant question about how that works. They would have like an abstract sense of time about like, you know, the past and the present and the future, but in terms of like a counting system of time, like how do you do that? So, you know, there's a lot there. I'm just like, oh, that's gonna get super super crazy and weird. So again, there's so much of this you can go into. There's too much, honestly. When I did the class on astronomy that I did at Clayton Valley, all of this was like 2 months. So just this conversation about habitability and alien life and how it could evolve, and this was like 2 months. So I can't do it all today. This video is probably already really long, and I'm not even done. I have another thing to go over. Yeah, there's so much, but there's a lot of this to look into. If you want a good place to start, habitable. The Wikipedia articles on habitable zone, Earth analog, which talks about like kind of what you need for a planet to be like the Earth, and also just like planet habitability. Those have a lot of potential ideas to get at. If you want a sort of sense of like, you know, what affects what, and also how you could think about this in terms of like, oh, if this was the case, how could this maybe affect the climate and stuff like that. There is actually a YouTube channel that the premise of the YouTube channel was basically if you want to create a scientifically accurate alien world as like a creation like kind of thing, like how could you kind of go about that using actually like math and data and climate information and stuff. It's called Artifexian. Here, I'll spell it out. It's that. That's very interesting to look into. They also do stuff about like creating your own language, which is its own thing that I'm not going to get into at all. So that's an interesting channel. There's another one that actually has gone into like creating an alien ecosystem. They've kind of started doing this. Crap, I think it was Biblaridian. I think that was what it was. It was something like that. The first video they did actually to just create the planet actually was with Artifexian, so you'll be able to find it from there. But yeah, so there's other stuff too. You get there's so much here if you know where to look, and I think this stuff is just so fascinating, and I could talk about this forever. But we have to move on, so I'm going to move on for now. But yeah, that stuff is there, and if you want to get into it, there's a whole wild world of this stuff, and it gets pretty crazy. But okay, so we have all these abstract ideas, all of this, maybe that, we don't know. Is there some way to get some sort of numerical value from this? Is there some way to somehow say, okay, based on this stuff, I think we should get a number that's blah? And this was sort of an idea that thought of by a guy named Frank Drake. He ended up creating the Drake equation. So the Drake equation is a thought experiment in which you, by assigning numbers to certain variables, one can predict. How did I spell predict that way? That was impressive. Predict how many intelligent civilizations there are in the galaxy. Okay. So it's a way of basically saying, okay, let's just put some numbers to this somehow and try to get some sort of an answer. Let's see how this works. So here was his equation, and this was made several decades ago. So n equals, that's right, it's r star times fp times ne times fl times fi times fc times L. Okay, that was the equation. So, and the idea was, if you have a number associated with all of these terms, you can approximate how many civilizations are in the galaxy. Now again, this is very much, it's not like an actual, oh, if you solve this equation, you'll know the answer. It's not the kind of framework. It's a way of thinking about this yourself and just putting some numbers to your own thoughts to just get some sort of an idea. Okay, this is never created as a way of like, this is the answer. It was never designed like that. But so we can go through these. Now, when this was first proposed, we did not know what any of these terms were. Okay, but as we've discovered things about planets and the universe, we kind of think we might know some of these. So let me explain what these are. So n to beginning is your answer, which is number of technologically advanced civilizations in the galaxy. Okay. That's what we're ultimately trying to solve for. So R star is the rate of star formation in the galaxy. Okay. Basically, how many stars are born in the galaxy every year? Okay. We know this. Okay, so this is something we actually know at this point. And the answer, the number for this seems to be about 2 stars per year. Okay. So that seems to be sort of the answer for that, about 2 stars per year. Now, granted, this is not constant, okay? As the universe and the galaxy ages, that number will go down, and eventually it will be 0, okay? But that's, like, within a trillion years. So we don't really have to worry about it right now. But, yeah. So as of right now, I think it's about 2. So, okay. FP is the fraction of stars that have planets, okay? And we did not know this, like, at all, because this was first proposed in, like, the 60s or something. This is quite a while ago. And because the question really was, like, are planets common, or are they rare? Like, we don't know. Do most stars have planets, or is our solar system a freak, right? We have no idea. And from what we have seen, from observations with the Kepler telescope, we think almost every star has planets around it. So, this number would be about 1. 100%, right? You think it's about 1. Again, does that mean every single star is a planet, right? No. But, like, basically, it seems that having planets around a star is the rule. It's not the exception, okay? Our star is not special for having planets. It seems that pretty much every star is a planet. It has at least a planet, if not multiple, around it. My throat's weird. So, sorry. Okay. So that's what we think from there. So those are the 2 numbers that we're pretty confident about. Okay? Those we can say, okay, we're pretty confident that's what those would be. From here, we get stuff that's a bit less confident. We get to NE. So NE is average number of Earth-like planets around a star. Now, this is complicated because your question is often, what do you mean by Earth-like? Okay? And we don't really know, right? And this sort of ties together with the next term, which I'll also put in. So FL is fraction of Earth-like planets that actually have life. And you can kind of combine these together because, for example, is Mars Earth-like? Right? You might think, well, no, it's Mars-like. But again, as I said, well, if you put a planet that was just bigger than Mars, where Mars is, it could have life on it, right? Is Venus Earth-like, right? Because again, going back to the image here that I had, Venus is just a little bit outside of the line. What if Venus was just a little bit closer in, and its atmosphere didn't get so crazy? Could it be habitable, right? And so we don't really know how this works really well, and so what this number could be. So basically, the way I think about it is that if you narrow NE down to a small amount, right? You need a planet that's very, very close to the Earth, then your FL number is probably kind of large, right? Because basically you're saying if my planet needs to be very similar to the Earth, then it's quite likely that it has life. But if my planet just needs to be kind of sort of like the Earth, then it's much less likely it would have life, right? So it's these numbers are kind of related to each other. I've seen that any sort of estimated from between like this number has been estimated to be from like 0.1, so meaning that like every 10 stars has an Earth-like planet, to maybe 3, so maybe like 3. So again, if you span the definition, so there's a pretty good range for this. Now, conversely, again, we have a fraction of planets that actually have life. Now, here's my take on this. And here's what a lot of people seem to say. And this is any life. Okay, this just means bacteria is fine for this one. Okay, and it gets to the fact that on Earth, bacteria and life evolved pretty soon, within a few 100 million years. And that's confirmed, right? A lot of like super old evidence from like near the very beginning of the Earth just doesn't exist anymore. So, and there's some evidence that I think that life is only like a couple hundred, like 200 million years old after Earth was formed, right? So, I think the oldest fossil that we have confirmed is about 700 million years after the Earth formed. I think it's about 3.8 billion, but there's some evidence that's maybe 4.2 billion. So, it basically, it seems that life formed very quickly on Earth itself. Great, again, that life was bacteria that was super weird, but it was life. And that's why I like to think, and I think a lot of people think this way, a lot of scientists, that if you have an environment that is decently close to Earth, it's quite likely you will have life. But again, usually that means like bacteria. But again, I've seen a big range for this. So I've also seen this number has been estimated to be from, again, I've seen some people argue it's still really small, 0.01 to actually 1. Because again, the idea is that like if you have a planet like the Earth, you're almost guaranteed to have some life, right? So especially if you've narrowed down NE so that your NE number is small, then this number, it makes sense that your number could be even close to 100%. So yeah. The next two though are complete unknowns. If Fi, which is the fraction of planets with life that develop intelligent life, and then similar that FC is also related, which is fraction of planets with intelligence that's develop. Originally, this equation was designed with a sense of what aliens can we like communicate with. So think about sending radio signals into space and stuff. So it was the developed communication technology. This is how it was originally designed. I like to think of it now as just like which planets develop like actual like a industrial technological civilization. But it sort of depends how you frame this compared to Fi. So similarly, Fi and FC are sort of related because also it's like, what do you define as intelligent, right? So I've seen some people talk about Fi as just like multicellular life, and just saying that that's the only step we're talking about here. But also you could, a sponge, you wouldn't think that's intelligent, but it's better than a bacteria, right? So like, is that the leap you're taking for that? Or do you mean like you actually need a human? Right, a human being with sapience, or do you want like a chimpanzee? Is that good enough? Or a dolphin, or a parrot, or even like an octopus? Right, those are pretty smart. So, or go back further in time, raptors, like dinosaur raptors. Those are quite smart for their time. So, where do you define intelligence? And then for FC, it's sort of where do you define technology? Right. So, for example, again, do you just mean they have a civilization? Because, again, how this was originally created was just like, can you send radio signals out in space? You could also clarify as, do you have the technology to leave your planet and actually explore space? Another one is just, do you have a technological civilization? Right? So it depends how this works. And so, for example, just like how NE and FL, I think, are kind of related, I think these two are related as well. Because, for example, if you say, oh, you need to develop like a human intelligence, well, that's probably like really, really small. But then you could argue, well, if you have a human intelligence, then it's just inevitable that they will eventually develop like space technology, right? In which case, then FC would probably be kind of large.
However, maybe you're arguing intelligent life is just animals, right? In which case, then what's the chance that they will develop technology? Probably very small, right? So they're sort of related in that sense too. But we really have no idea about these numbers. So we really have no idea. But most people, and this is for this argument for FI, I've seen two main arguments. So actually, I'm not even going to argue that. I'm just going to say we really have no idea. Here's the two main arguments is to be, again, whether this number is bigger or smaller. The smaller argument is, look how long it took, right? Again, I said how life began on Earth relatively quickly, but then it was like 3 billion years before we got from one bacteria to a sponge. Okay, so and then it took like less than a billion to go from a sponge to us. Okay, so one of the arguments here is that like it seems that step of like going from single celled to multi-celled was a really hard step to get to. It took a long time. And that's like 3 billion years of like nothing catastrophic happening, right? And maybe another planet could take a little bit less time, but that's still at least a couple billion years where you can't have like an enormous asteroid impact or some horrible, solar flare. You know what I mean? There has to be a decent amount of time of no horrible disaster. And even then, people also argue like, okay, even if you get to like animals, well, think about how many animal species have been alive. Only one of them ended up getting to like true intelligence, right? So like the chance of that, who knows? But the other argument I've seen is that it's sort of an inevitability thing. It's that life has just always progressed to be smarter, and it took a long time, but some sort of intelligence is like inevitable outcome eventually, right? So that's another idea. Again, we don't know. I could argue either way on this, and I don't have a good idea about this at all. And then also similar with this here, we have no idea for this either. And again, it's related to FL, right? Or FI. If you define intelligence as humans, then I could see argument that, well, FC is probably fairly large. But if you are talking about intelligence in terms of animals, then I can see FC being very small. So it's, who knows? Then L is average lifetime of a technological civilization. Okay. And we don't know about this. We have no idea about this either. I've seen so many numbers thrown around. I've seen, 100 years, 1,000 years, 10,000 years. I've seen billions of years. So, because here's the idea. There's a couple main things about this. One argument is that it's actually probably kind of small because, we developed space travel and radio communications less than 100 years apart from developing nuclear weapons, and climate change is happening, so that could be problematic. So one of the ideas that people might just kind of destroy themselves, like not too much after they figure this stuff out, in which case the lifetime is really short. I've seen other arguments though that once you're advanced enough so that you can leave your planet, like permanently leave it, then your lifetime is all of a sudden like almost infinite, right? Because once you can leave your solar system, I should say leave your solar system, because if you can leave your solar system, well then what's stopping you, right? Because then, okay, go to another planet, another star system. Oh, you mess up that planet, okay, just go to another one. You can just keep going, and then you would last for trillions of years. So, and again, maybe 99% of them don't make it that far. But if one of them makes it that far, well, then you have all the time in the world to literally expand throughout the entire universe. So, this is a giant question for this here. And again, you could make so many different arguments for this, whichever you want, and how this could work. So, yeah, there's so much here. There's a way to think about and all this kind of stuff. And if you multiply all these numbers together, you would theoretically get an answer. So that's what I want you to do. Your wrap-up question is, again, think about each of these terms and just think about what a number would be. Just come up with some sort of reasoning in your head about, I think this number could be this, and then multiply them together and show your result. Again, just think about it. Think about it, and there is no right answer, okay? There's no right answer whatsoever. Well, okay, R star should be 2, and F should probably be 1. But then the other numbers, again, in some range for this, but then this, we have no idea. So just see what you can come up with. I'm gonna share what my best guess is, but again, it's a guess. It's purely a guess. I have no better authority than anyone else on this. You do not have to have my answer at all. I'm actually curious what you can get. Now you may get a number that's like less than 1, and you may think, well, wait a minute, but we exist, so like the number shouldn't be less than 1. So the idea is that if you get a number that's less than 1, especially if one that's like way less than 1, that means that almost certainly we're alone, right? And we were some random fluke that just happened to occur. So that's kind of the sense of that there. So see what you come up with. I'm curious to see what your numbers are for this, because you can have a giant range. But you can have, I've seen answers that are like a trillionth, very tiny. I've seen numbers like I've seen like, a billion. So yeah, I'm curious to see what you can come up with here. All right, so here's my guesses. Again, purely a guess on my part. I don't have any real authority on this. Okay, so R is 2. FP is 1. Okay, so NE, I'm going to argue that NE is actually, I'm going to argue that for this, my sake, that NE is quite close to Earth. It's like Mars, no. So I'm going to narrow this down kind of a lot. So I'm going to say that NE is actually 0.5. Okay, I'm going to be kind of small on that, which means that actually I'm going to say a fraction of Earth has life on it. I'm actually going to go large. I'm going to do something that you might think is weird. I'm going to say 1. I'm going to say that if you have a planet that's pretty close to Earth, I'm going to say it's almost a guarantee there will be some life on it in some manner. But then you get to the issue of intelligent life. And I'm going to say intelligence as like early humans, so like Homo sapien, that kind of intelligence. I do think I see both arguments here, the sort of inevitability over time, but also you need billions of years of no complete total disaster. So I don't know. I'm going to do that. Maybe. I don't know. It's so hard to say. I could see so many arguments on that. But then for intelligence to the communication, I'll say, I think, okay, once you have like early humans, I could see it kind of being an inevitability that we could get some to communication technology. Maybe not 100% inevitable, because I could definitely see like, maybe you have like hominids like Australopithecus and stuff, but then they end up going extinct, and that could be fairly reasonable. Maybe that ice age, for example, could have been worse. There's an idea that there was a supervolcano eruption about 10,000 years ago that might have reduced the entire Homo sapien population in the world to like 1,000 people. So, yeah. So in that case, I'll give it 0.1. And then average lifetime technologies, I have no freaking clue. I'll say 1,000 years. I have no idea. That's a complete random guess. I have no clue. Okay, so let's multiply that all out then. So we have 2 times 1 times 0.5 times 1 times 0.001 times 0.1 times 1,000. 0.1. Okay. So this would imply that we are alone in this case, in this example. I don't know. I don't know. I don't have any good authority of these numbers. I just made this kind of up on the spot. Here, okay, and I said it before that I had this sort of gut kind of feeling in what I like. So one of the main arguments as to there not being intelligent life is that, well, we should have seen it by now. And you may think, well, the galaxy is a gigantic place, and we've only, looked at a very small portion of it, which is totally fair. But, for example, there is an argument where you could build a small probe, like very small. Think like, maybe not microscopic, but like, like the size of a computer mouse or something, and that and because it's so small, it can travel very fast. Not at the speed of light, but honestly, like 10% of it or something, pretty dang fast. And what it can do is that once it gets to another solar system, it could sort of like attach itself to an asteroid that has like metals and stuff in it, and it can sort of build another copy of itself. Okay, and then it could send that copy out to another, and sort of then it could build a copy. So you could basically spread out and make copies of it yourself as you keep going. And if you do that, even if you're moving in like 10% the speed of light, because of the exponential effect of making copies of yourself, then the copies make copies and etc., you can actually get a probe around every single star in like a few million years. So then the question is like, well, then why isn't the galaxy swarming with probes if there aren't like, civilizations around. And I have two arguments for that. One is, um, okay, and so anyway, there's one specific argument against that exact example is how do you think that we would be able to detect something that's like the size of a computer mouse? Like, if we have something that's that size and it's like, in the asteroid belt, like we wouldn't see that. Or if it's like, maybe it could be around Saturn, we would not be able to see something that small, right? It's just, we don't have the technology to see that yet. So how do we know, right? Like, they aren't already there. We just couldn't see them. Um, and again, that's something that like humans could theoretically do like now almost. We have like the tech to build something like that. We just, it's very cutting edge, and of course it would take a lot of resources, and again, we wouldn't see any return for it for like thousands, if not millions, of years. But it's not something that's like some insane, crazy sci-fi tech that could happen. So that's a fair point. Also, I would like to say that, like, sure, the universe has existed for 13.7 billion years, which a lot of people point to saying that, like, well, we've had all this time. So even if, for example, let's say there was a civilization that began just a million years before ours. A million years. That's not that much long. That's not very long ago, again, considering the timeline of the universe. That would mean it's a million times more. That's a million years more advanced than us. Like, what kind of crazy crap could they get away with? And how would we not notice something like that? They'd probably arrange that, and that's fair. But another thing is that, in terms of the entire life of the universe, like that it will have, the amount that we have explored that has happened is unbelievably tiny percentage. It's like there's a video that I want to show you later that kind of gives you that percent, but it's a lot of zeros before you 0 point lots of zeros percent. So one of the arguments is that there could be a bunch of intelligent life, but we might just be one of the first ones, which is also fair. But here's what I like to think, and that is that in order to have an interstellar civilization that actually can effectively explore and exist in multiple star systems, the speed of light is too slow. The speed of light is too slow. It's, again, for us to get to the nearest star at the speed of light, it's 4.2 light years away, I think, something like that. And that's the nearest one. That's not economically viable. You could maybe send out some missions and like a probe or something. That's one thing. But to actually have a civilization that expands through multiple star systems, the speed of light is too slow. You wouldn't be able. Why would you have like an actual, like civilization, colony, whatever, that's so far away that for you to even send a text message to somebody, it would take like 9 years for you to get a response, because like 4.5 years to get there, 4.5 years to get back. Like that's not a thing. So the speed of light sucks. It's too slow. So in order to have some sort of interstellar civilizations, you need to somehow figure out how to beat the speed of light. And we're going to try to talk about this a little bit more later, actually. But of course, we do not know how to do this in terms of like, this is the tech, build it, boom, we do it, right? We have no idea. But if you could do that somehow, then all of a sudden the cosmos is yours, right? So I like to think of it as, because in that same sense, we've been sending radio signals out and looking for radio signals, but that's just light. So the analogy I've heard is it'd be like setting up a telegram, going into the middle of the desert, setting up a telegram and waiting for telegram messages. And then after you're not getting anything, say, oh, well, I guess there's no humans alive on the Earth anymore. No, we have a better method of communication. We have, So my thought is that, like, let's assume there is a way to break the speed of light, and we figure that technology out, and once we start dealing with that, it will be like all of a sudden we've come online. Okay, it'll be like all of a sudden you brought the Wi-Fi router to the Amish community, right? All of a sudden, like, oh, there's people everywhere, but they've just been using this stuff that's like way more advanced than us that we didn't even know was there, right? Again, think about like cavemen, right? And even if they that live again, think about like the uncontacted like tribe people in like the Amazon rainforest, right? They don't know that like Wi-Fi signals and cell phone signals and 4G, 5G, whatever is all racing around the globe. They don't know that because they're just not even there. So. You know what I mean? Like that's sort of my optimistic viewpoint, and I think that's sort of a nice idea. Also, it's a way of sort of, if there is like a galactic community of civilizations or whatever, it's sort of a nice gatekeeping tool, because it's like, oh, now that you join the club, right? You beat the speed of light, you figured out how to do it, now you're good enough. Now we'll come and talk to you and figure out what to do, and, you know, hey, what up, homie? You know what I mean? So, like, that's sort of my optimistic and I think somewhat reasonable idea, but that's not a fact-based analysis, okay? It's just sort of like, here is a scenario that could be true because I want it to be true, okay? I have no idea. Nobody knows, okay? There's so many arguments one way or the other. So speaking of which, this leads me to your homework. I want you to write sort of an argumentative essay, whether you think intelligent life would be rare or common, okay? And I want you to think about, again, not just stuff that I've talked about, but also stuff that you could sort of look up on your own. So you have, again, there's Wikipedia pages. I've given you examples of habitable zone, Earth analog, planetary habitability, Drake equation. There's arguments for like all of the terms as to what kind of numbers they would be. And I want you to really kind of give some sort of, take a stance and think, I think intelligent life would be rare because blah. I think it would be common because blah. And I want you to give several examples. There is no right or wrong answer because we don't know. And so I want to kind of see what you can come up with. Again, people, I think, I don't know, I like to think that it's at least common enough, but nobody knows. Nobody knows. So that's kind of the sense of that there. Definitely curious to see what you can come up with for this, though. So, yeah. Okay. Again, I could talk about this for so long. I didn't even get to anywhere about, like, okay, if we assume aliens exist, what might they look like? That's a whole other giant conversation that could take forever, which we just don't have time for. But there's a bunch of stuff you could look at for that as well. Yeah, I'm afraid to look how long this video is. But hopefully it was at least somewhat interesting. Again, if you're curious about like the habitability and sort of like how planets sort of could exist that's like similar to Earth but different, the Artifactsian channel I think would be very interesting for you to look into. If you want some sort of way of thinking about actually like designs of aliens, again, I think it's Biblaridian. I think that's what it's called. I don't remember. They're doing an active thing, which is sort of creating their own ecosystem. It's very interesting. They have like 3D models of stuff too. It's very well done. And I'm sure there's other projects there as well. Yeah, there's just so much. And this stuff, like, if honestly, like this content right in here, just this whole talk about aliens and like design of planets and design of aliens, if I could like have like a perfect job for me, it would be like this kind of like creative and scientific thought process for me. Like just coming up with this stuff, designing this stuff, and like that would be what I would want to do with my life. But that's not really a thing. So unless you can somehow make enough like YouTube ad revenue for it or whatever, then, and also you know how to like create 3D models of things, which I don't know how to do. So yeah, but like this is like my thing. Like I love this stuff. So yeah. Okay. This is a long batch of stuff. All right. What are we at right now? I guess, I don't know. I'm stopping this. Hopefully this wasn't horribly, terribly insane.